So next thing I want to do is talk a little bit more about the details of functions. We're going to see a few different things in section 3.2. We're going to see, domain and range. We're going to see rates of change. But first, I want to show you some example functions, some well-behaved, useful, applicable functions that we can take as just examples. I'll call these the 9 toolkit functions. Later, we'll be building other functions out of these, so these will come back. All right. And I have a list of them, but I wasn't turned to that page because I'm well prepared for things. Okay, so I'm going to just name each function and then show you its graph. So there's a constant function. Like h in the previous lecture, this is a function like this, where c is just some number. So it could be like f of x equals 2 or f of x equals -5. So no matter what input I pick, it always has the same output. Let's say the output is 2. Then there would be points like 0, 2, and 1, 2, and 2, 2, and 3, 2, and 2.5, 2. No matter what input you pick, the output is always 2. So the graph of this function is just going to be a horizontal line at 2, or whatever the value of c is. So that's the constant function. Not much more to say about that. It always has the same output, so it's not super exciting. Next, I want to talk about a linear function. We saw linear equations before. That was equations where x didn't have any exponent. So like 3x plus 2 or x minus 4 or just x. I'm going to start with the simplest one. Let's say f of x is just x. Sometimes this is also called the identity function because the output is the same as the input. So think about this. When the input is 1, the output is 1. When the input is 2, the output is 2. When the input is 3, the output is 3. So I've graphed 1, 1, 2, 2, and 3, 3 here. But that works in the negatives as well. No matter what input I give, the output is the same. So the graph is going to look like this. Later, I'll be building any other linear function we could possibly want. We can build out of this one. I'll show you how to do that in section 3. I want to say 3.4 or 3.5. I forget which now. But that's in unit 3. So we'll get to that after the second test. Might as well talk about absolute value as a function here. So previously we've seen this as an operation or as a grouping symbol. It's kind of dual purpose. But here I want to say the output of this function is just going to be the absolute value of the input. So the way absolute value works, it's distance, but right now the way I want to think of it is when you give it a positive number, like 5, it gives you 5 back because 5 is 5 units from the origin. So it's got points like 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. If you give it a positive input, it gives you that same number back as the output. But when you give it a negative number, like let's say you give it -2, that's 2 units away from the origin. So it's just going to give you a +2. -1 gets you a +1, -3 gets you a +3, -4 gets you a +4, like here and here. If it would update. There we go. So the shape of this graph, it's a V shape. Whoop, I screwed that up. Try that again, but nice. There we go. That's good. I'll make a quadratic. I'll just start with the simplest one, and then we'll build other ones out of this later in unit 3. Let's do f of x equals x squared. That's as simple as a function can be and still be quadratic. So 0 squared is 0, and 1 squared is 1. 2 squared is 4, so I'll plot 2 comma 4. And 3 squared is 9. That's actually off the graph here, so that's way up there. So the further out you go, the faster it's increasing. So it's getting steeper and steeper. That's why it kind of has a U shape. And when we go negative, 0 squared is 0, but then negative 1 squared is 1 again. Negative 2 squared is 2 again. So this graph is actually symmetric about the x-axis. We'll talk about what that means in 3.5 as well. Yeah, it is 3.5, where we'll build other functions out of these. We'll also talk about how to tell when a function is going to be symmetric horizontally like this. We call that even symmetry. And you might be able to guess why, but I'll give the exact definition later. Next function is cubic. So this is, you probably guess what this one does. It's like the quadratic, but instead of x squared, here f of x is going to be x cubed. So 1 cubed is 1, 2 cubed is 8, so this is getting steep even faster than the quadratic. It's going to curve way up steeply there. Now negative 1 cubed is negative 1, and negative 2 cubed is negative 8, because not all the minus signs cancel. 2 of them cancel out and the third one stays, right? So the other half is rotated from the first half instead of flipped. So it's the same shape, but rotated. Oh, this is a weird one. I'll call this the reciprocal. F of x equals 1 over x. This one has a pretty goofy shape, so. So 1 over 1 is 1, and 1 divided by negative 1 is negative 1. We'll start there. 1 divided by 2 is 1/2. 1 divided by 3 is 1/3. So I'll plot those points here. 1 divided by 4 is 1/4. 5 gives you 1/5. So it's getting closer and closer to the x-axis, but it's never actually going to reach it, because you'll have 1/6 and then 1/10 and then 1/100th way out there. We call that an asymptote. This is asymptotic behavior. Don't worry about that too much, though. We don't study that in any detail, but it's a line that it's approaching, but never going to reach. I'll tell you more about that later. Right now, we're just trying to get the shapes of these functions down, because these are our toolkit functions. These are the basic functions that kind of give you an idea of how different functions might behave in this class. You notice they're all pretty nicely behaved. They're nice, simple shapes, relatively simple at least. If you've seen fractals like the Mandelbrot set, you know how horribly complicated shapes in mathematics can get. You know, for those of you who haven't seen it. I have to pull this up real quick. Compared to shapes like this one, the shapes that we're studying are very simple. And you know, as you zoom in, this thing is complicated on every scale. No matter how much you zoom in, it's still just as complicated as it was before. So pretty cool shape. Shapes we're studying, on the other hand, are very simple shapes. Being simple means that there's a lot of different places we can apply them, and they're still complicated enough to have a lot of explanatory power. So it's kind of the perfect compromise. Now check this out. 1 divided by 1/2, so this x value right here, 1 divided by 1/2 is just the reciprocal of 1/2. It's 2. So I get a 2 here. 1 divided by 1/3 is 3. 1 divided by 1/4 is 4, and so on. So what I get is this weird swoosh shape. Oh, geez. Trying that again here. There we go. That's a pretty good one. It's not perfect, but it's pretty good. You get the idea, yeah? I'm going to try one more time. Jeez. This is easier on a whiteboard. So it's this basic swoosh shape. If I take 1 over -1, I get -1 instead, and in fact, the whole swoosh shape is copied down here. Guy messed that up. Just not happy with these terrible swooshes I'm drawing this morning. Here we go. That's pretty good. Okay. Ooh, sun's almost up. Let's see. Next thing I'll do is, I guess I'll call it the reciprocal squared. So this is going to be f of x equals 1 over x squared. On the right-hand side, instead of 1/2, 1/3, 1/4, I get 1/4, 1/9, 1/16. So it's going to be the same, but steeper, like this. On the left-hand side, we're going to take all these values, and these are just the same as these values, but with a minus sign. But when you square them, the minus sign goes away. So for example, if x is -2, I get 1/4. If x is -1/2, I get 4. So that's the reciprocal squared function. Now let's get back to some more normal shaped functions. The last two are the square root and the cube root. So how this works is, remember, okay, so when I talk about functions in this class, I mean real valued functions. All of our functions in this class are going to be from the reals and to the reals. There are never going to be complex numbers in functions in this class. Complex numbers are in this class only as the solutions of quadratics or other polynomials. Now, as a matter of fact, you can define complex valued functions. They're just beyond the scope of this class. So in this class, when I'm taking the square root as a function, I'm just going to say we can't take the square root of a negative number, not because we don't have a way to do that now, but because it wouldn't be on the graph. This is a graph of real x values on the horizontal and real y values. It's a Cartesian plane, not a complex plane. So the first number I can take the square root of is 0, and then the square root of 1 is 1, the square root of 4 is 2, the square root of 3 is 9, and so on. Oops, daisy. So we can't take the square root of negative numbers in this context because they don't show up on the graph. Those are complex numbers, and there's no way to plot them here. As a matter of fact, I'm going to draw this one more time. My goodness, I just want these functions to look nice. That's a lot more accurate. There we go. The square root function is actually exactly the same shape as a parabola, but only half of one and sideways. We'll talk more about why that is in Unit 4. But I think you might be able to guess. Just like the parabola would have, the parabola has 1, 1, 2, 4, and 3, 9. The square root has 1, 1, 4, 2, and 9, 3. Because it's the opposite function. The inputs and outputs are switched. So there's some concept called inverse functions that has to do with switching the inputs and outputs that we'll talk about in Unit 4. And finally, the cube root. Where's my marker? The cube root, f of x equals the cubed root of x. So this is the opposite of x cubed, like the cubed root of 8 is 2. I talked about fraction. Okay, I forgot. I did these in section 1.4. I was worried for a second that I'd accidentally skipped them, but I've been going from my notes this whole time, so I'm sure they're in there. Sorry, just doubted myself for a second. So the cubed root of 1 is 1. The cubed root of 8 is 2. -1 gives -1, and the cube root of -8 gives -2. So this is actually the graph of x cubed, but sideways. Pretty cool. And those are our 9 toolkit functions. We'll come back to these throughout the rest of this unit and learn more properties about them. But for now we have what we need. So the next thing I want to talk about is domain and range. And I'll talk about that right after the jump. Let's make that a separate video.